Before I begin this, I want you to think about what you have in common with everything around you. This can be your chair, a random object in the room, or even what you're watching this video on. I'll give you a few seconds to think. Can't think of anything? I'm not surprised. A human being has nothing in common with, say, a lamp, right? Well, actually, they do have one thing in common. In fact, you have one thing in common with everything that's currently around you. You are made of matter. And so is your chair, and that random object in the room, and even what you're watching this video on. It's all made of matter. Everything that you're able to hold or touch can be considered matter. But what exactly is matter? The definition of matter is anything that has mass and takes up space. The laptop that I'm writing this script on, the desktop that I'm editing this video on, the device you're watching this on, and even though you can't see it, the air you're breathing right now can all be classified as matter. Not everything is matter though. Light and sound, for instance, like the light produced from this video or the sound of my voice narrating, are not matter because they don't have mass or volume, as opposed to air, which does have mass and volume. Speaking of air, it's also known as oxygen, or more simply, O. Oxygen is an element. It's a substance that can be broken down into smaller substances chemically and are the most significant part of everything that is matter. The tiniest unit that keeps an element's chemical properties together is simply known as an atom. Atoms are made up of three different things: protons, neutrons, and electrons. All three fall into the category of subatomic particles, or in other words, particles that make up an atom. Protons and neutrons are located in the center of an atom, in the area known as the nucleus. Protons have a positive charge, while neutrons don't really have any charge at all, hence their names. Both protons and neutrons are pretty much the same size and mass. Zooming out, we find a tiny cloud of particles circling the nucleus. These particles are called electrons. Unlike protons and neutrons, electrons have a negative charge, are far tinier, and are located outside the nucleus. Altogether, atoms almost never have an overall charge. This is because of atoms almost always containing the same number of protons and electrons, causing the negative charge of electrons to cancel out the positive charge of protons. It can be better understood when we take, say, lithium, for example, and adding up the combined charges of its protons, neutrons, and electrons. Lithium has 3 protons, each having a charge of positive 1, so we can place positive 3 in our problem. Lithium also has 4 neutrons, but since neutrons don't have an overall charge, they don't have any real value. So, let's add 3 by 0. Finally, we have electrons. Since lithium has 3 electrons and electrons have a charge of -1, we can subtract 3 from our current equation. Now, we can determine the overall charge of an atom with some basic math. 3 plus 0 equals 3, 3 minus 3 equals 0. We'll come back to the structure of atoms later on, but back to elements. Every element is made up of only one atom, with every atom containing a different number of protons, neutrons, and electrons. However, the number of electrons in an element is normally determined by how many protons are in the atom. Take an atom of helium, for example. Helium has 2 protons in its nucleus. Therefore, it also has 2 electrons outside of its nucleus. But what about neutrons? Well, they can have different numbers of neutrons, which can create entirely different forms of a certain element, but more on that in a little bit. Because an element can only contain one type of atom, it makes every element unique. Every form an element is in is still made up of its own atoms. For example, copper wire is made up of copper atoms. Diamond and graphite are just 2 of many different forms of carbon, but each form is still made up of carbon atoms. Elements are represented by 1 or 2 letter symbols that are used globally. The symbols are mostly either a single capital letter, such as oxygen, O, or a capital letter followed by a lowercase letter, such as lithium, Li. The only exception to this rule is with newly discovered elements, such as oganesson, Og, formerly known as ununoctium, UuO. Each symbol is placed on the periodic table and organized by their atomic numbers, the number of protons in an atom, their mass numbers, the number of protons plus the number of neutrons in an atom, and their chemical properties, such as transition metals, nonmetals, metalloids, and others. Mass numbers are often interchangeable with some elements. This is called an isotope. Isotopes are atoms that have the same number of protons but a different number of neutrons in comparison to other atoms of the same element. They don't have different chemical properties than other atoms of the same element, since isotopes have the same number of protons and electrons as other atoms of their element, but they do have different masses. Isotopes vary in mass in comparison to each other due to the differing amount of neutrons. Let's take hydrogen, for example, which has 3 different isotopes. All 3 of them each have 1 proton and 1 electron. However, the most common hydrogen isotope, protium, doesn't have any neutrons. Since protium has 1 proton in its nucleus, it has a mass number of 1. A second isotope, deuterium, does have a neutron in its nucleus, along with 1 proton. Therefore, its mass number is 2. The third isotope, tritium, has 2 neutrons this time, along with 1 proton. Therefore, this gives tritium a mass number of 3. Isotopes also can be sorted by how common they are. An isotope can exist in 2 forms, stable and unstable. Stable isotopes are isotopes that do not decay into other elements, while unstable isotopes can and will decay into other elements. Unstable isotopes continue to decay until they reach a point where they are stable. Unstable isotopes can be determined by having 1 or 2 more neutrons than protons in an atom. Let's go back to tritium, which, again, has 2 neutrons and 1 proton. Since tritium has more neutrons than protons, it makes it an unstable isotope, which can decay over time. Therefore, this makes tritium the least common of hydrogen's 3 isotopes. The time it takes for half of an unstable isotope to decay is known as its half-life. These half-lives can last anywhere from as little as several milliseconds to as long as millions of years. For example, let's say 100 grams of a certain isotope has a half-life of 5 years. If that 100 gram substance was left alone for that long a time, you would return to only find that 50 grams of the substance was left. 5 years later, only 25 grams would remain, then 12.5 grams, then 6.25 grams, then 3.125 grams, and so on. So, if the half-life of the 100 gram substance is 5 years, how much would be left in 50 years? Well, the answer is pretty easy to figure out. All you have to do is divide 50 by 5, which will leave us with 10, meaning that the isotope would have to go through 10 half-lives. Therefore, we would need to divide 100 by 2 a total of 10 times, which will then leave us with approximately 0.098 grams left of the substance after 50 years. For a real-world comparison, tritium has a half-life of about 12.32 years. So, 1 gram of tritium would decay by 1/2 every 12.32 years, from 1 gram to 0.5 grams to 0.25 grams, and so on. Let's go back to carbon for a little bit. Remember earlier when I briefly stated that carbon has many different forms, including diamond and graphite? Well, included in those forms are carbon's many different isotopes. In total, carbon has a total of 15 different isotopes, only 2 of which are stable, carbon-12 and carbon-13. Carbon's unstable isotopes have relatively short half-lives for the most part, ranging from a mere 30 nanoseconds with carbon-21 to as long as 20.334 minutes with carbon-11. However, the one exception is carbon-14, having the longest half-life of every carbon isotope by far, spanning a ridiculously long 5,700 years. We'll come back to mass numbers later. In the meantime, let's talk about molecules. Atoms can join together to create molecules, or the smallest unit of a substance that behaves like the substance. Not all elements can form molecules, however. Neon, for example, has elements that are found uncombined in nature. However, most other elements can form molecules containing more than one atom. Molecules can vary in size and in number of atoms. Compare glass and plastic, for instance. A molecule in plastic contains thousands of atoms, all vibrating together to keep the plastic in one piece. Meanwhile, when we look at a molecule of glass, we can see that there are only 3 atoms inside of just one molecule. Therefore, a glass molecule is much smaller than a plastic molecule. This is why a plastic cup doesn't break when it's dropped, when a glass cup can shatter into pieces. Now, after hearing everything I've discussed so far, some of you may be wondering, what's the mass of these atoms and molecules? Well, we determined that through a term known as atomic mass, literally the mass of an atom or a molecule. It's used to find the average masses of elements or molecules, represented by the Unified Atomic Mass Unit, or U. To give you an idea of how tiny the mass of an atom is, a single atom of fluorine is less than 1/1,000,000,000 of a billionth of a gram, or, in scientific notation, 1.0 times 10 to the power of negative 21 grams. Since these tiny masses are so difficult to work with, an atomic mass is often expressed in atomic mass units. 1 U is equal to 1/12 the mass of an atom of carbon-12. Since carbon-12 contains 6 protons and 6 neutrons, hence the name carbon-12, each proton and neutron has a mass of about 1.0 U. Electrons aren't included in an atomic mass unit, as they are far tinier than protons and neutrons and therefore don't contribute a lot of mass to the atom. On the periodic table, the atomic mass shown is the average atomic mass for the element found in nature. It's a weighted average. In simpler terms, carbon isotopes have a greater effect on an atom's mass than more rarely found isotopes. For example, chlorine has 2 isotopes, one which makes up 76% of all chlorine on Earth, while another makes up only 24% of all chlorine on Earth. The more common of the two clocks in at 35 U, while the less common of the two clocks in at 37 U. Therefore, because the chlorine isotope with a mass of 35 U is more common than the isotope with a mass of 37 U, the average atomic mass of chlorine is closer to 35 U, or about 35.453 U, as listed on the periodic table. Please note that calculating these values together don't give you an exact answer of 35.453 U because of rounding. But after saying all of what I've just said, you're probably confused as to what any of it had to do with matter. What do elements, atoms, molecules, and mass have to do with matter? Well, as I said in the beginning of this video, matter is anything that has mass and takes up space. Atoms, although incredibly tiny, still have mass and still take up space. The elements of those atoms, whether they be a metal or a non-metal, still have mass and still take up space. Molecules, made up of atoms, still have mass and still take up space. And mass is one of the words that defines matter. Things, as in objects, are made up of atoms. Things are mostly made up of molecules. Things are made up of one element, or many elements. Things have mass, and things take up space. So really, the answer to the question of what everything I've discussed in this video had to do with matter is, well, everything. Obviously, there are a lot of other factors that apply to atoms, elements, and molecules, but I won't get into them today since this video would go on for far too long as a result. However, there are a lot of good sources out there for you to learn more about what matter is and how it works. As I finish this video, I leave you with some sources I suggest. Thank you for watching.